Hello and welcome to Coffee Table Physics. I'm Riley.
And I'm Jonathan. The reason you're probably watching us right now is because you wondered, like us, how do fridges actually work?
It turns out that the magic cold box in the corner of your kitchen works on a fairly simple 5-step process using a substance that is, funnily enough, called a refrigerant. The piece of physics we're about to talk about is known as thermodynamics, which describes things such as heat and temperature.
Step 1. In the compression chamber, a piston moves down, sucking in the refrigerant, currently a gas. The intake valve then closes and the piston squashes the gas, raising its pressure as well as its temperature. By the end of this process, our refrigerant is in a funky phase of matter called a supercritical fluid, meaning it acts a bit like a gas, but also a bit like a liquid. Because this process doesn't involve any heat transfer, we call it adiabatic, a very special type of process in thermodynamics. It's also reversible, meaning we could return the system to its original state with no net change in heat or work done on the system.
Step 2. The refrigerant is pumped through coils at the back of the fridge. This is known as isobaric to physicists, meaning it's held at constant pressure. In thermodynamics, heat always flows from a hot object to a cold object. Now, because the refrigerant is hotter than the surrounding air, heat naturally flows out of the refrigerant and into the air, and so it cools. This is the same as my cup of coffee warming my hands, as the coffee is hotter than my hands. If you've ever put your hand down the back of a fridge, you'll feel it's rather warm.
Step 3. The refrigerant, now a liquid, is forced through a nozzle and expands as its pressure decreases. Now, this is a special type of expansion known as Joule Kelvin expansion, and so the temperature drops dramatically. A way of thinking about this is because the refrigerant molecules are further apart, but intermolecular forces are trying to bring them back together. As the molecules move against these forces, they lose energy. It ends the stage as a mixture of liquid and gas.
Step 4 is the crucial stage in how a fridge works. The now very cold refrigerant is pumped through the inside of the fridge, the bit where you put your food, often through pipes in the back wall. Because the refrigerant has a much lower temperature than the inside of the fridge, heat naturally flows out of the food and into the refrigerant. This is just like when you hold an ice cube. Heat flows from your hand and into the ice cube, and so your hand feels cold.
Which brings us on to the final step. The refrigerant passes through the expansion valve. Its pressure drops and it evaporates to become a gas once more. So, we can see, over the course of this cycle, the net result has been to essentially suck heat out of your food and deposit it at the back of your fridge unit.
The process we've just talked about is a special case of what is known as a thermodynamic cycle, where the start and end state are the same. If we run a fridge backwards, what we would have would be very similar to an engine.
One property that we want when we're choosing refrigerants is that it has a high latent heat. Now, latent means hidden, but what do we mean by hidden heat?
If I'm heating a pan of water on a stove, I'm supplying heat to the water at a constant rate, and so I will see its temperature rise at a constant rate.
Until its temperature reaches 100 degrees C, or 212 degrees Fahrenheit. Then what I will see is heat being supplied to my water, but its temperature showing no change whatsoever. Where's it going?
At this stage, the liquid water is boiling and becoming a gas. In doing so, intermolecular forces are being overcome. This requires energy. The amount of energy to completely vaporize the water is the latent heat. But why do I want this in my refrigerant?
When the refrigerant passes through the inside of the fridge, it vaporizes, meaning it absorbs heat at a constant temperature. We want this to be large, as we want to suck as much heat as we can from our food. If you're interested, the refrigerant currently used in fridges is a chemical known as HFC134A, 1112 tetrafluoroethane.
And so we reach the end. Now next time you're cracking open the beers, you'll know what's keeping them cool.
Thanks for joining us. If you have any thoughts on the video, feel free to leave them in the comments box.
Plus, tell us if there's something about this wonderful world around us that you think, I want to know what's going on here. We would love to help.
See you here next week.
Same time, same place.
Cheerio.